So there's one more topic we need to cover on Knapsack before we can leave it behind for a little while. And that's the topic of its complexity. So let's think about the complexity of this algorithm for Knapsack. All right, so we've seen already an exhaustive search algorithm for Knapsack. And the exhaustive search algorithm was at least as bad as 2 to the n, right? And why is that? Because it had to enumerate all the subsets, potentially up to all the subsets associated with a knapsack problem. And there's 2 to the n subsets, right? So exhaustive search is this clearly exponential algorithm. So exhaustive search was, and I'll say big omega of 2 to the n. Recall big omega is like a floor, right? It tells us a lower bound for the complexity. So we're saying the complexity is at least as bad as 2 to the n because we have to enumerate all n subsets. Practically, we're going to get something that looks like n 2 to the n because, you know, for each subset you also have to add up the values of the subset and stuff. But it's clearly exponential. Okay, so now number 2, the DP algorithm, regardless of whether we use top-down or bottom-up, the DP algorithm is big theta of n times w, right? Which looks like a polynomial time algorithm, right? So the exponential, we haven't talked too much about the distinction between polynomial and exponential, but exponential is, and if you don't know this and have intuition for this already, the exponential is clearly not polynomial time, right? 2 to the n is not polynomial in n. This clearly is, right? This is polynomial in n, and it also appears to be polynomial in w. So I say appears, and you may be confused about this because, you know, there's no obvious way that it isn't polynomial in w, but I'll say appears polynomial in w. Okay, so that's a fact, right? It's very clear that the complexity of this algorithm is n times w, right? And we're done, right? That's the complexity. Okay. So here's the very strange rub in this whole thing, and we haven't talked hardly at all yet about this concept, but we have this concept in algorithms that we'll get into some good detail in later in the course, that says there is a class of problems, in fact a huge class of problems, for which no polynomial time algorithm is known. So we'll say, and we call this class the class of NP-hard problems. So the class of NP-hard problems. It's a class of problems, not a class of algorithms. So NP-hard problems means that no polynomial time algorithm is known. No polynomial time algorithm is known. Okay? So that's fine. You know, you can accept that there exist problems that we don't know how to solve fast. We don't know how to solve in polynomial time. But here's the very strange thing. The knapsack problem is NP-hard. The C in there is NP-hard. Right? This version of the knapsack, right, with no modifications, the 0-1 knapsack is NP-hard. So the question for you to chew on, and maybe to pause the video and think about and see if you can find a way around it, is how do we reconcile these two things? These points 2 and 4 on this slide look like they contradict each other, right? On the one hand, point 2 here says, look, we have what appears to be a polynomial time algorithm to solve the knapsack problem. And down here, I'm claiming that no polynomial time algorithm for the knapsack problem is known. What's going on? Well, let's think a little bit about what it means to say polynomial in n and w, okay? And what it means to say a polynomial time algorithm, okay? So let's think about let's think about things very, very carefully in terms of the size of the input. So those of you who are in automata at this point, you may already have some kind of intuition for this. If not, hopefully by the end of the course you will. But when we talk about a polynomial time algorithm, what we mean very, very specifically is polynomial in the size of the input. Okay? So a polynomial time algorithm, or I'll just call it a Polytime algorithm as an abbreviation. So polynomial time means polynomial in the size of the input. All right, what is the size of W? So, suppose I tell you W is 351. W is that the capacity of the knapsack is 351. Right, what's the size of that number? Well, you look at that and you say, Brown, you're going off the rails. That's 351. That's how big the number is. And I'll say, no. The value of W is 351. Right, so the value of W is 351. The size is 3. Right? Why 3? Because it takes 3 digits to write it down. Okay. So when we talk about the size of numbers in terms of algorithms, and especially when as they relate to algorithm complexity, we mean not the value of the number, we mean the size of the representation of the number. And it turns out that the relationship between the size of a number and its value is exponential. Okay? So if I write the number 351, what is the size of that? Well, it's 3. So it's logarithmically related to the value of W. Right? So it's related, 3 is related to the logarithm base 10 of the value of W. Okay, so the size of W, let's write it like this, is related to the logarithm, if I'm thinking in terms of decimal numbers, the logarithm base 10 of W. And in particular, I believe it's the floor of the log plus 1 or something like this, right? So yeah, that would be correct, I think. The floor of the log plus 1, because if I say I added on another 0 here, then the size would be 4, and the logarithm of this thing would be something just greater than 3, right? So the log of 3510 is 3 point something. And because it looks like 1,000, times something less than 10. And so that's the log of this. The floor of the log of this would be 3, and then plus 1 gives me the size. Let me back up just so that I don't have this thing cluttered for posterity. Right, but so the size of the W is related to the logarithm of its value. And so what does that mean about the value as a function of its size? Well, that means that the value of W is related to the exponential of the size of W. So it's related to, again, if we're thinking in terms of decimal, it's related to 10 to the power of the size of W. Okay, and so now let's go back to the algorithm complexity of the knapsack algorithm, the DP knapsack algorithm. So the DP knapsack is big theta of n times W. Well, what I just wrote right here is that W is proportional to the exponential of the size of W, of the representation. And so if I want to think about the capacity of the knapsack as being something that takes up space in memory, it takes up exponentially as much space as the number is large. So what this equals, right? What big theta equals is n times something times, like, let's call it 10 if we're pretending that we're representing numbers in decimal, 10 to the size, or I could say the number of digits of w, right? Or I could write it like this. I could say it's big theta of n times 2 to the number of bits of w. In either case, the algorithm is still exponential in the size of the input, right? The actual representation of the input. And we call this thing a pseudo-polynomial complexity when it is polynomial in the value of the input, but exponential in the size. Okay, so this is it's a term that you'll run into sometimes as you're thinking about algorithms, and the term is pseudo-polynomial, where it's polynomial in the value and exponential in the size. Of the input. Okay, and so there's a lot that we can learn. There's a lot that we can learn from the knapsack problem, and from DP algorithms for the knapsack. Right, we can get a feel for how DP works in general. We can also get a feel for how memoization, or the memory functions approach, works in general, and how the top-down approach versus the bottom-up approach can relate to each other. And then we also get to learn about this concept of a pseudo-polynomial complexity for an algorithm, right? Polynomial in the value and exponential in the size. So if you can guarantee that the values of your capacity aren't too large, then we actually have fast algorithms to solve the knapsack problems. The issue is that they will never be linear, at least as long as, and we'll get to this, as long as p doesn't equal np, they'll never be linear in the size of the input, or even any kind of polynomial in the size of the input. Always exponential in the size of the input. And so we'll revisit this concept of pseudo-polynomial later in the course when we start talking about the various classes of NP-hard problems, right? There's actually a close connection between having pseudo-polynomial algorithms and being strongly or weakly NP-hard, and having approximation algorithms of a certain kind and approximation schemes and things like this. So there are some interesting connections here that we're going to exploit later on in the course. But for now, you've learned something about complexities, and you've learned something about some of the subtleties that we run into when we're talking about NP-hard problems.